Hello everyone. So this is a question from JEE Mains 2026 28 Jan evening. The question is, which of the following reaction is not correctly represented? Okay. So this is an important one, which is wrong technically. So the chapters involved in this question are hydrocarbons and amides. Okay. So let us look at the first option. So we have this organic compound and we have the reagents as Br2 in the presence of H nu or light, and we are getting this as the product. Okay, so the first thing that we need to look is that we have bromine and we have H nu. So this is going to be free radical bromination. So this is free radical bromination, and I will give you some data about free radical bromination. So what happens is in free radical bromination, we break a CH bond and we, create free radicals. So we, obviously this can be connected. So we get this and we get, so this is the first initiation process. I mean, initiation is obviously, Br2 is becoming Br radical, and then we break this organic compound and we form this radical. Okay, so I have some data. If you have a 3-degree carbon which is connected to a hydrogen, to break this bond to form a free radical, the energy required is 93 kilocalories per mole. Okay, if you have a 2nd-degree carbon attached to a hydrogen, to break this and to get a free radical, the energy required is even more, 96 kilocalories per mole. And to break a 1-degree carbon which is attached to hydrogen, to get a free radical is even more, that is 100 kilocalories per mole. Okay, so continuing this, if we have, this is very interesting. If you have a allylic carbon, that is C double bond C, which is not a part of a aromatic system, C double bond C connected to a C and that connected to an H. If we want to break this and make free radicals, the energy required to break this is 89 kilocalories per mole. And if we have a benzylic CH, that is a benzene ring, and a carbon attached to a hydrogen, if you want to break this and create benzylic free radical, the energy required to break this is 90 kilocalories per mole. Okay, so this data is very important in the sense the benzylic, that is this case is allylic and this case is benzylic. Okay, so benzylic and allylic CH bonds are weak and they can be easily broken compared to tertiary CH, secondary CH and primary CH. Okay, so this is an important statement, that is benzylic and allylic CH bonds, they are weak. Okay, and they are weak for a reason. Okay, because when we break them, we create free radicals. Okay, and the free radicals formed as a result are resonance stabilized. Okay, so the benzylic and allylic free radicals are resonance stabilized. That's why it is easy to break them, because the free radicals that we are getting are very, very stable because of resonance, are resonance stabilized. Okay, so I'll give you an example. For example, let's say we have this. So we created a allylic free radical. This guy is resonance stabilized. How? So this can form to become a double bond here, and this double bond can break to, and this can form a free radical there. So it will ultimately result into a double bond and this. So you can see here, this free radical and one electron from this double bond became this double bond, and one electron from this double bond became the free radical. So this is resonance stabilized. So this makes the benzylic and allylic free radicals extremely stable. So we have to look out for them if there is any. So because of this resonance stabilization, okay, if we have benzylic and allylic CH bonds in the molecule, or in the organic compound, they will be preferentially brominated over, the tertiary CH or secondary CH or primary CH. Okay, so let us look into the question. In the question, let us draw this guy again, that is this CH3. So here we can see that there are allylic positions, because this is a double bond and this is a carbon, and this H is one of the allylic hydrogens. This is a double bond, this is a carbon, and this H is one of the allylic positions. Okay, so this is one allylic hydrogen, these are another allylic hydrogens, right? So therefore, in the presence of Br2H nu, as I told you, since the allylic free radical formed are resonance stabilized, so they are preferential, they are preferred over the tertiary CH or secondary CH or primary CH. Okay, so therefore, two different kinds of allylic hydrogens are available, so two kinds of free radicals can be formed. Okay, so either we can break this first, so it will then result into CH3, and like if you break this bond, one form the free radical, so therefore I am representing a dot there, right? And this, or it can also result in the breaking of this bond and forming a radical there. So we can get the this as one of the free radical, that is CH3 and H here. Yes, so out of these two, as you can see here, this free radical is resonance stabilized, yes, but it is also connected to 1, 2 and 3. So this is a tertiary 3-degree free radical. And let us look at this. This is resonance stabilized, yes, but it is connected to 1 and 2 secondary. So therefore, this is the major product. This is the major free radical. Okay, and then Br radical will come and attack and form a bond there. So therefore, the answer is going to be CH3Br double bond. So this is the major product that we are going to get. Okay, and let's see what they have got. So they have got CH2Br, which is not correct. So they have, therefore this is the wrong product that they have got. Okay, let us look at other options. So instead it should be, the correct answer should be CH3Br and a double bond there. Okay, let us go and look into the other options. So the other options are, so this is the second option. So where we have a diazonium salt, this is basically benzene diazonium chloride, and we have Cu2Br2 in the presence of HBr, and we are getting bromobenzene. This is an example of Sandmeyer's reaction. Okay, in Sandmeyer, so this is an example of Sandmeyer's reaction. So in Sandmeyer's reaction, we have a diazonium salt. So let us take an example of benzene diazonium chloride, N plus triple bond NCl minus, and there can be three kinds of Sandmeyer's reaction. If we have CuCl HCl, if we have CuBr and HBr, and if we have CuCN and KCN. So here we will get chlorobenzene, here we will get bromobenzene, here we will get CN and the benzene ring. Okay, so therefore this is the correct answer, no issues with that. Okay, let us go and look at the third option. Third option may, again you can see there is Br2H nu, so there is going to be free radical bromination. Okay, and I told you that in free radical bromination, allylic and benzylic cases are preferred because they result into allylic and benzylic free radicals which are resonance stabilized. Okay, so always look into the possibility of the presence of a benzylic hydrogen or a allylic hydrogen. Okay, so here obviously allylic not possible, because in allylic the double bond should not be a part of the aromatic system. Okay, so here allylic not possible, but here benzylic possible because double bond single bond H. So you can see this double bond is a part of the aromatic system and it is attached to a carbon which is attached to a hydrogen. So this is a benzylic hydrogen. Okay, so if we draw this C H H H double bond. So these are, you know, benzylic hydrogens, and if we break them, it will result in into the formation of a benzylic free radical, which is resonance stabilized. So it will result into the formation of, let's say we break this and we get a free radical CH H and a free radical here. So this is, you know, resonance stabilized. And then you know, initiation is, we are going to get Br free radicals, and this guy is going to come and react with this to form a product like this. So we get CH Br and the benzene ring, right? So CH2 Br, yes. So this is the correct product that they have formed. Okay, so this is correct. And let us go and look at the fourth one. In the fourth one, we have toluene, and there is Br2 again, but we have iron, okay, and we have dark. So this dark tells us that, okay, there is no free radical formation possible. Okay, and also the presence of iron tells us that it is going to be electrophilic substitution. Electrophilic substitution. So because iron can react with Br2 to form FeBr3, which is a Lewis acid, and this FeBr3, you know, it polarizes the Br2, excess Br2 molecules. It can react with the excess Br2 molecules, and it can polarize it or create poles to result in the formation of a complex like this. So can you see this part of the Br has a positive charge now? Now this part of Br can go and attack our toluene. Okay, why? Because this has positive charge and this guy has loads of pi electrons. Can you see? So therefore it is kind of attracted towards the aromatic toluene. Now, can you see the presence of an electron donating CH3 group? So it is a alkyl group, and alkyl groups are electron donating groups, and electron donating groups are OP directing. Electron donating groups are OP directing. That means this guy, that is this R group, this directs the Br plus into ortho positions and para position. So therefore the product that we are going to get is CH3 Br in the ortho position and CH3 Br in the para position, right? So these are the two products that we are going to get. Obviously this is the major one because, you know, less steric hindrance. So therefore let us look what they have found. Ortho and para bromotoluene. So yes, ortho and para bromotoluene, correct. This is also correct. So therefore the question is asking us to find out which one is wrongly marked. So D is correct, C is also correct, P is also correct. So the wrongly marked one is A. This is wrong. Instead of this, this should form. Okay. So the correct answer is A. Okay. Thank you.